This is a snapshot of nuclear power around the world. I pulled this information from the IAEA database, it's International Atomic Energy Agency. So you can see there's about 440 power reactors operating around the world right now. So there's 95, I believe, is the number to date in the United States. So that's a good bit of the global fleet right inside the country, and 50 or so are under construction right now. Um, the U.S. is the top power producer, followed by France, China, Japan. These are the real players when we're talking about nuclear power, um, both in terms of number of reactors as well as actual electricity generated from each of the stations. But as far as share of nuclear power for that country, the U.S. is kind of far back, mostly because the country is very big and there's a lot of demand. So despite having the most reactors, only about 20% of the power for the United States comes from nuclear. For France, it's more than 70. A lot of other European countries, smaller countries especially, that might have, Russian type reactors or whatever, their shares might be very large, but they may only have a couple of units. And that's only just because they're a small country. Something to notice on the top right-hand side is this plot of where these plants are. No surprise, America, Northern America, in Europe, and Asia have a lot of um, power under operation today. But if you notice, there's a light blue bar added to each region that shows what's under construction. Look at the North American under construction bar. It's a sliver, right? So really, this technology is getting um, implemented in other parts around the world, even though it seems sometimes on our shores that nuclear is having a hard time sticking around, and new builds are very expensive and delayed. But realize that other countries are very interested in developing nuclear power and are building at a pretty fast rate. Um, Down below, something to just take a glance at is the little plot on the bottom right. So it shows you the age of these reactors. You look, a lot of them are 30 years or older. More than half are 30 years or older. So, these plants were largely designed and built in the 60s and 70s, at least in the United States. And so keeping them online and operating for their original operating license, which is 40 years, is very important. And then after they reach that 40 years, as many of you know, the plant owner, the utility that owns that plant, can apply for a license renewal to the NRC. So that could be another 20 years license, taking them to 60 years. After that, they could do it again, what's called subsequent license renewal, SLR. And they can go from 60 years to 80 years. And there's no real hard limit. So if you've got these big power reactors online, it's in your best interest to keep them running, because they've got a long life, and they can generate great carbon emission or zero carbon emission power for your grid. This is a little video, hopefully it plays. I'll kind of let it do its thing. Um, you can find this on the IAEA's website, the Power Reactor Information System, PRIS, and it shows you a little map of the world and where the plants are deployed. At the top you can see the number of units in each country. The UK had a lot of gas-cooled reactors. There's a lot of information on this, so I won't go through everything that we're seeing here, but you can really see how, you know, in the 70s and 80s, nuclear power really blossomed all around the world. Later on, through the 90s, somewhat stagnates, especially in the United States. Watts Bar Nuclear Station, it's about an hour drive from AMS. The Unit 1 on that site was finished in 1996, and Unit 2, we helped bring that one up online in 2016. And those two are the youngest power reactors in the United States. So it kind of gives you a snapshot. I mean, 1996 is a long time ago, and 2016, 20 years separates those two units, and they're very old technology. What we're looking for in the future are advanced reactor designs that, you know, need to be deployed in the next 10 to 20 years in order to make up for retirements in the current fleet. So now you can see in this, a good takeaway is look at how much Southeast Asia is projecting to build. So it's no surprise that the rest of the world is interested in nuclear technology and likely going to, you know, sustain the fleet, and hopefully the U.S. continues to at least build a few, you know, light water reactors as well as advanced reactors. There's a little map down in the A lab, and here's a little snapshot of it in this slide. Most of you probably already know, give or take, where these plants are. You've probably been to several of them. You can see on the eastern part of the country, most of these plants are located. There's a few out west, but it really well positions AMS. So responding to calls to some of these sites is not a huge ordeal for us. I'm going to talk a little bit about these specific reactor technologies. All of the plants in the United States right now are called light water reactors. This is the type of power plant that they are. I'll have a couple of slides on these, and really a very basic overview of what is a pressurized water reactor, what's a boiling water reactor. Pressurized water reactor is the most common type in all over the world. And generally speaking, when you see this slide about PWR, most PWRs are basically the same. They have those major components. So those are the vendors that supply these, at least in the United States: Westinghouse, Babcock and Wilcox, and Combustion Engineering. And then I believe every BWR is a General Electric. You can see this is an up-to-date statistics on the reactors in operation today. So 95, that's still quite a bit. Only 2 under construction. If you've been to Vogtle, you've seen the construction site. Vogel's Unit 3 and 4 will be Westinghouse AP1000s. So those are the only 2 under construction in the entire country. At one point, there were going to be a couple more at the VC Summer site in South Carolina, but that project got scrapped. You know, we've got jobs where we go to China and we test instrumentation and control system sensors and equipment at their AP1000s. So the only 4 operating Westinghouse AP1000s are actually in China. And just for your reference, I also included a little plot. If you want to see, you know, well, I know about 20% of the power that comes from, or that comes to the United States comes from nuclear. What are the other sources? This comes from, I guess, last year's data. So you can see nuclear is a good chunk of that. Renewables has grown up over the course of the past several years, sure, but you know, still within that, nuclear is a big supporter of clean energy. So in this slide, I've got a snapshot of some of the owners of these power plants, these utilities. These are our customers. In the blue, I put PWR plants. In green, those are boiling water reactor plants. You should obviously know who you're going to work for when we go on site. And if you ever want to reference it for your own information, you've got this slide now available to you. You can see in the bottom left-hand corner which states get majority or a large portion of their electricity from nuclear power. So Tennessee's up pretty high on that list. The plot on the map on the right-hand side, is probably no surprise there, where the states are that have a large share of their power coming from nuclear. So we'll get into the specific reactor designs. I started with boiling water reactor because this is really, I think, the most basic and simple thing to start with. So everything that's in that diagram below, is a major component that you should just be familiar with. You don't need to know, depending on who you are, maybe you need to know more or less than somebody else, but as long as you know in general at a high level what's going on, that might be sufficient at least to start. So within the containment structure, the containment building, you've got the reactor vessel. Okay, within this vessel, you've got your fuel, right? It's not like a fossil plant. You've got hydrocarbons getting burned. No, it's uranium, right? That's the fuel, and it doesn't burn, right? You're fissioning it with neutrons. You're hitting neutrons at the uranium 235 isotope. It fissions, it splits apart, and that releases heat. So within the reactor vessel, you have a core that's made up of all of these bundles of fuel. And when it's generating heat, you've got water that's inside this vessel. And for a boiling water reactor, that water is boiling and getting turned to steam. It leaves the reactor vessel and it goes as high energy steam to a turbine. So it spins the turbine. The turbine's connected to a generator, and that's what gives you electricity. And as it goes through that turbine, it's losing its energy. It'll pass through a condenser where you've got another loop of water that's just cooling down that circuit so that the steam turns to water. Then that can be pumped back into the reactor and repeat the cycle. So the water is really doing two major functions. It's keeping the reactor cool so to speak. It's the coolant, but it's also the working fluid, the heat transfer mechanism to make something useful out of that energy that's created inside the core. So what we do is we test sensors and instruments and things that are monitoring that fluid, that coolant. They might call that the process. Okay, if you hear the word process, that's what that means. For a boiling water reactor, measuring pressure is very important, among many other things. In general, these reactors, almost any reactor really needs to measure things like temperature, like pressure, level, flow, and neutron flux, of course. So those things are instruments that we may test, either the instrument itself, or maybe its cabling, or other components that have safety significance to the plant. You might hear the term mode 1 through 5. If you ever want to know what does that mean, here's a little table on this slide for your reference. You probably hear it a lot more when we go to PWRs, because we're typically on site while they're coming back up after a refueling outage. So for boiling water reactor work, it's mostly cable testing, so it may not be as significant to know the modes, but there you go. You can jot it down in your notes and have it in your back pocket. So we'll move to the PWR. So you can see it's pretty simple, or pretty similar, right? It's not quite as simple, and there's just one more circuit of water. So pressurized water reactor, as the name implies, the primary circuit of water, reactor coolant system, you might say, is kept under very, very high pressure because you don't want to boil that one. You want to keep it as a liquid, right? So with that circuit, the primary circuit kept under extreme pressure, we're talking 2,000 pounds per square inch, more than that. That's going to prevent the water from boiling. And it's going to do the same sort of thing. The water goes in through the core in the reactor vessel. It's serving to both keep the core relatively cool so that it doesn't overheat and melt down, and take the heat from the core and send it to a steam generator. So it leaves the reactor vessel, it gets pumped through a little loop of pipe that we call the hot leg pipe, and it goes to a steam generator. And as it goes through the steam generator, it's losing temperature, it's losing that heat, it's transferring it to the second loop of water, which I'll talk about in a minute. And when it's cold, it's leaving the steam generator. It's cold. I say cold. It's probably about 570 degrees Fahrenheit. It will get pumped back into the reactor vessel via what we call a RCP, reactor coolant pump. So it returns to the core, and it does the same thing over and again. It just keeps doing this. That's its little cycle. And a PWR may have 3 or 4 of these loops, okay? So the second loop of water is the water that is turning to steam, spinning the turbine, and doing the work. So instead of like a BWR, where you're using the same reactor coolant water to spin the turbine, for a PWR, you have a separate, physically separated loop, okay? So that's called the secondary system. And really all of that is very similar from plant to plant. Even a conventional, like a gas or a fossil plant, will have the same type of what's called balance of plant. That's all of the machinery that's non-nuclear, if you will. So I don't know if you guys can see my cursor, but anything that's basically here, or really inside the containment structure, you might hear people say the nuclear island, right? That's what makes it a nuclear plant. Everything on the outside is really industrial. You know, you could find that in another type of plant, because all these components are sort of have nothing to do with the reactor. I'm generalizing, but you get the picture. And again here, you know, you can jot down this table of operating modes, or you can reference this slide in the future. But if you've gone on a few outage trips to PWRs to do either cross-cal or CRDM testing or rod drop testing, you've probably heard these modes before. So it's a good thing to know these. And excuse me. Most of the time we don't talk about mode 6 because we're usually never there. But mode 6 is when they've actually dismantled the reactor vessel and they're doing refueling. We're usually not on site at that time, so you may not be familiar with mode 6, but there's the info for your benefit. This slide gives us a little bit of a more detailed view of a PWR circuit. So we'll start on the left. You can see you've got, in this case, a 4-loop system. You only need one pressurizer, and that's a component that is helping to regulate the pressure in the primary system. And you only need one of those, and it's usually piped into one of the loops on the hot leg. But you can see there's 4 loops. They each have their own steam generator in this case, and everybody's got a reactor coolant pump. There's 3 in there. One of them's hiding behind the steam generator, but 4-loop plant should have 4 reactor coolant pumps. And you can see in the middle figure, we've got a cutaway of a reactor pressure vessel. There's a lot of stuff going on in there. We don't need to focus on everything, but obviously we care about the core. If you've seen, we've got a couple of little model fuel assemblies. They're down in the A lab. If you haven't seen them yet, come find me and I'll point it out to you and we can talk about it a little bit. But they are little mock-ups. They're little fuel bundles, and inside that is where you'll find little pellets of uranium oxide, and that's the fuel in these types of plants. At the top of the reactor vessel head, for each control or shutdown rod, there are several important assemblies, or at least very important for us. The first one I've highlighted in red there, that's the CRDM assembly. So that stands for Control Rod Drive Mechanism. And we also have one of those down in the A lab that you can see. It's very big, very heavy. And the photograph right here, if you can see my cursor, here are the CRDM assemblies. And inside these blocks, that kind of looks like 3 blocks for each one, are coils. And one of the tests that we provide is to measure the timing and sequencing of the energization of these coils. And that sequencing is going to let the operators know that the system is operating the way it should, that it's driving the rods up or down into the core as appropriate. If you don't know, a controller shutdown rod is one of the main sources of reactivity control. So if you want to shut down the plant, you lower, or if it trips, they fall, because energy to the CRDM coils is removed and they release the rods and they fall by gravity into the core. And the rods are made up of a neutron absorbing material. So that's what's stopping the reaction from taking place. Now it needs to happen fast. You know, we measure the drop time before they go back online after they restore the top of the reactor vessel head, and that shutdown time needs to take less than 2 seconds, right? But after that has happened, the reactor doesn't become cool. It's not very, very cold. It's still very hot. I liken it to turning off the stove. You got a boiling pot of water on the stove, you turn it off, okay, great, but it's not safe to touch, right? It's still hot. So at the very least, you need to shut that power off first. So what happens when the reactor trips is that these CRDMs basically shut off. And when they shut off, the rods, it's kind of hard to tell in here, but you can see each one has got like a long channel. These rods will drop the control assembly into the core. And there you go. That's how you shut down the plant. On top of this CRDMs, we have a similar thing. We've got a series of coils in an assembly called RPI. That's rod position indication. Those coils have a different function. Those are what tell us, or the operator, where the control rods are located. If the reactor if the control rods are removed from the reactor, then they will indicate a signal to either our test equipment or to the operators so that they're removed. And when the CRDMs are de-energized or the plant trips and the rods fall by gravity into the core, signals from the RPIs are what we use to watch, so to speak, them fall. Okay? So you can kind of see the RPIs in this picture here. In this case, there are many little coils. In another system, they might be like a single coil, they have different versions depending on the plant, but they essentially perform the same function. Rod position indication, so it gives you the position of each rod. So we test both of these coil assemblies. You can see in this picture, they've removed the top of the vessel head from the reactor. In this picture to the right, you can see in order to do the refueling, they flood this whole cavity. Okay, because water is a very good shield, and this fuel is spent, but it's still hot, both from a radiological standpoint and from a temperature standpoint. So the water is good to help keep that relatively cool and to shield everything. So you can see here with the head off, they can access the fuel. Here's a better picture below it, and they can get there's a little crane and some robotics. They can move the fuel assemblies around. They can shuffle them if they want. They can put fresh bundles of fuel in here, and then to store the spent fuel, they will actually move it through a little canal, and it will go live for a while in what's called the spent fuel pool, and that's basically where it lives for a long time until it can be moved to a dry cask for storage. It's kind of like a sarcophagus for these things. Okay. Okay, I'll just briefly mention a CANDU design. This is another water-cooled plant, but it's what's called a heavy water-cooled reactor, pressurized heavy water reactor. CANDU, Canada Deuterium Uranium. As you can imagine, this is a Canadian design. It uses heavy water, which is very similar to water. You don't really want to drink it, but it's a different isotope of hydrogen, that's all. This is a very unique type of reactor. It can be refueled online. It doesn't have a reactor vessel like a PWR does. It's got what's called a calandria. This picture right here shows you the calandria and the size of it. Look at this man, he's very small compared to the whole size of the calandria. And this is like, in each one of these, if you can see it, there's little tubes. Each one of these tubes will be several fuel assemblies, and once this is connected into the plant, little pipes will come to each one of these tubes, and these will be like several individual series of water, and the coolant, the heavy water in this case, that goes through there does the same sort of thing that we were talking about in the other plants. It picks up the heat from the core, in this case it's the calandria, and then you pump that water away to a steam generator. So from the diagram down here, you can see the plant. A lot of this other equipment is the same, right? You've got a steam generator, you've got a turbine, you've got your generator here, you've got a condenser, and it does the same sort of loop. That's the secondary loop, just like the PWR's secondary loop. The main difference is our calandria, which can be refueled online. I don't have a great picture, but you can kind of see there's a robot here, and when the plant is online, they can use similar machines to actually open up one of these little fuel channels at a time and push in a new fuel bundle while at the same time kicking out a spent fuel bundle on the other side. Another machine similar to the refueling machine will basically capture the spent fuel assembly and then transfer it to the on-site storage facility. So that's a very, very unique and important feature for CANDU plants, that they can be refueled online. Another great thing about this type of plant is that they can be maintained over a long life, because a lot of these components can be replaced. It's really difficult to do and it's expensive, but it's doable. Whereas a pressurized water reactor, you really can't replace the reactor vessel. But the calandria itself doesn't function the same way. So you can replace the tubes and certain components over the life of the plant. Um, and one of the benefits of this type of reactor is that you can use natural uranium. So when you mine for uranium, it's mostly U-238. It's just an isotope of uranium. The fissile material is U-235, but a CANDU plant doesn't need to enrich that. So that's a great plus. Most of these are obviously in Canada, and then there are several other countries that have either CANDUs or copies, essentially, of CANDU's pressurized heavy water reactors. Okay? All right, so now this is something that everyone should at least be familiar with, a small modular reactor. We have a project on SMRs, so please know the term SMR, know what a small modular reactor is. Excuse me. So there have been small reactors in the past, research reactors, first-of-a-kind reactors. They're not technically a small modular reactor. When we're talking small modular reactor, we're talking about a power reactor, something that you would use to generate electricity. To be small, we're talking less than 300 megawatts electric. To give you some reference, a big pressurized water reactor is probably around 1,000 megawatts electric. So small is less than 300. That's pretty good for replacing things like fossil plants, aging fossil plants that may be going offline as we go to a more green-friendly energy future. Modular. So what does that mean? That means that these things can be built in a factory. They're small enough to fabricate the whole reactor vessel and other major plant components, and then take that via a truck or a barge or rail or whatever to wherever the site is going to be. And that's going to, lower the cost to construct one of these things. So big enemies of nuclear say, oh, well, it's too expensive to build. It takes too much time. And they're not wrong. It is. So what can you do? Well, you can standardize your reactor design, which is something that if you've gone to these plants around even the country, made by the same big boys like Westinghouse and GE, they don't look the same, right? So if they had just built standardized plants, they could probably reduce some of their cost. So this is aiming to capture some of that. And because it's so small and can be transported around, you're going to have it better suited for remote locations, islands, places in like Alaska where they have mining communities and things like that. The military is interested in really even smaller reactors than this. And they're unique. They're trying to incorporate some new features that add to the safety of nuclear. I put here a simple diagram of what it means to be an integral reactor. So you all now know what a steam generator is, and you've got your loop of pipe here, you've got your reactor coolant pump, and it's kind of separate components, all kind of linked together. Well, an SMR is small, and you can design it such that all of the major components are integrated into the reactor pressure vessel. So that's a great design feature, but it creates issues when it comes to sensors and instrumentation. That's one of the issues that we look into on our project, is that although this is a very sleek and nice design, it eliminates certain accident conditions. It creates a host of problems as it relates to everyday issues that we deal with, maintenance and operation of these types of power plants. All right, so this is a little visualization of what we're talking about when we say small. So this, again, is a PWR. This here is our big containment building. You can tell this is a for loop PWR in this diagram. It's probably about 1,000 megawatts or so. Reactor vessels here. We've got our loops running to different steam generators, our reactor coolant pumps, and everything. So this is pretty big. And of course, there are a lot of other buildings and equipment on the site, but this is all the nuclear island here. For an SMR, NuScale, for example, this is a company that we're working with. This is their whole containment. The whole thing is here. Everything that's in this right-hand side has been reduced to this footprint. You can see the size of I guess like a 6-foot tall person would be. Within this containment vessel, not a building, but a containment vessel, we've got the reactor vessel. So it's like a can within a can, we say. And this is containing the primary system. There are no pumps, and this is using basically physics, natural buoyancy driven flow to operate the plant. This is a passive design. Okay, very, very sleek, very nice, but really, really compact. And so it doesn't have a lot of room for sensors and other instruments and cabling and things like that, which causes problems that we're looking into. This is a more simplified drawing of an integral SMR. I mentioned there's no coolant piping, so that reduces the possibility of what's called a loss of coolant accident, LOCA, LOCA. That's something that you should be familiar with. That's basically what it sounds like. Maybe there's a leak or something, you're losing coolant, you have the opportunity to uncover the core and melt it down. That's the worst case scenario. So just be familiar. If you hear someone say LOCA, now you know what it is. I mentioned no pumps. You can see that this is a very sleek design, but from a maintenance standpoint, it can be very difficult to access. You can see here, after the reactor has been delivered to the site, it's going to be loaded up into a little bay. You can see at this site, they have the ability to house up to 12 of these modules. You can see this is one side. You have to imagine on the other side of this giant reactor building, there'll be 6 other modules. And they're all generating only 60 megawatts electric each, but that's 720 total. That's not a bad size for a whole plant. But they're only going to have 24 months of operation for these types of reactors. Very similar to what we have today, 18 to 24 month refueling cycles. As such, if you have a site with 12 of these on, that's really every 2 months you're in an outage. So you're going to need to streamline everything associated with the operation of these types of things in order to really get the benefits of this type of technology. You can see here in the picture, they've got a crane. They will do their refueling by dismantling the outer containment vessel in this cradle here, and then they can dismantle the reactor vessel here and refuel using this machine, this little crane, and put the spent fuel in this pool as necessary. Then they and cables or what have you on it, and they could do any maintenance in a docking area as necessary. But when they want to go start the reactor back online, they dunk it back into this pool. They'll have to basically reassemble the plant and start up. But if there's any issues with it, they'll have to, maybe repeat this process and do manual INC work, which, becomes a huge pain. So we're trying to work with NuScale in particular under our project to help address some issues as it relates to both sensors and their low voltage cabling. Okay. All right. Now we're looking at microreactors. Take the essence of an SMR and make it even smaller. So instead of 300 megawatts, we're talking less than 20. Again, you want to use passive safety however you can. There are certain designs that use what's called heat pipe technology. I won't go into that in this slide set, but we can talk about that if you're interested. And these are really of interest to the Department of Defense. They're thinking that they want a self-contained system that can power like a forward operating base, so they don't have to rely on diesel and trucking in diesel, and then it's a target for attack and things like that. So if they could just put a whole self-contained reactor in a shipping container and plop that onto a site, have it generate electricity or maybe even heat or use that energy for other purposes, that'd be great. These things can be designed such that they are online for many years, for 10 years without refueling, or maybe they don't refuel at all. You just replace it with another microreactor once it's been spent. So these are a few developers I put on this slide. If you're interested, Google some of these names or listen into some nuclear news bulletins, and you'll probably come across several of these developers. All right, so I'll talk a little bit about advanced reactors. I'm not going to go through each generation, but all of the plants that we deal with the exception, I think, of just the AP1000s, all of them are Gen 2s. So PWRs, BWRs that are around the world today are largely Gen 2. Okay, Gen 3 is AP1000. It's very standard, similar to its old school Westinghouse PWRs, but better. Has passive safety features and nice new capabilities. But it's largely similar to a Gen 2 reactor. What's on the horizon the next decade or so? The development of what's called Generation 4 advanced reactors. So about 20 years ago now, a forum was developed with experts to determine what should be considered an advanced reactor, the next generation. They had goals of things like sustainability, improved economics, safety, reliability, all of those things. And with those goals in mind, they came up with several reactor designs that generally are considered advanced or generation 4 reactors. They're of different neutron spectrum, use different coolants, can be open or closed fuel cycles, and they can do things that we all want nuclear energy to provide the world. So what are these terms? What are fast neutron spectrum? I'm going to go over that in the next few slides very simply. So thermal versus fast reactors. LWRs use thermal spectrum. So what you've got here is your fuel. It's a fissionable material, right? Something like uranium 235, plutonium, whatever. Something that can sustain a chain reaction with neutrons. So if the plant is using a moderator, that could be water or graphite, a neutron is going to get slowed down by the moderator. So it's going to collide but not get absorbed, and it's going to slow down, and when it slows down, it's going to be more likely to create or to hit a uranium-235 and fission it, so split it, right? So when it's thermalized or it's slowed down, and it's more likely to fission the uranium-235, you can use pretty low enriched fuel, 3 to 5%. Natural uranium is like 0.7% U-235. Most plants use 3 to 5% enriched uranium. If you have a fast reactor, then that means there is no moderator. So these neutrons are bouncing around. They're going really fast. They're not, losing their energy, and they're not likely to fission a U-235 if it's enriched so low. So to compensate for that, a fast reactor needs to use a higher enrichment so that it's more likely that the fast neutron is going to hit a U-235 and fission it. You need it to fission because that's going to release heat, right? And that's what we want. So that's all we really need to know about those. Okay. Breeder reactor. This is an interesting thing. A breeder reactor is basically a system that can produce more fissile material than it's consuming. So, the core of the breeder will produce, excess neutrons that can be used to convert a fertile material that can be something like uranium-238 or thorium-232, and that can convert to a fissionable material like plutonium-239 or uranium-233. So then that converted fissionable material can then be removed from the core, you can reprocess it, and you can actually use it again as fuel in another reactor. That's a pretty interesting technology. Traveling wave reactor is basically that, but it's converting the fertile material into fissile material within the core, and then using that fissile material as its own fuel without having to remove it and reprocess it in some external facility. So it's like traveling wave as it's kind of burning through the reactor, if you will. It's breeding and burning its own material. So that enables it to operate for a very long time. Okay. I've really simplified this. You can find more detail on open and closed fuel cycles online, but this will give you what you need to know, I think. We're not really fuels people, so this should be sufficient. But you've got the open, or what's called once through fuel cycle. This is where you mine for the uranium, you enrich it, you put it in a centrifuge. You basically are trying to increase the amount of 235 uranium-235 in the fuel. Then you've got to fabricate it and basically make it into these assemblies. And then it goes into the reactor. It operates maybe 18-24 months. After it's done, it's spent fuel, and it's stored either on site for in the spent fuel pool, or eventually in some kind of dry cask sarcophagus type of thing, and that's done. So it's radioactive for a long time. It's bad, and enemies of nuclear say, well, this is a problem. They're not wrong, but you can reprocess that fuel. You can take spent fuel and reprocess it and actually use it in a different kind of reactor and sort of, burn it again, if you will. After that's done, you've got some wastes. That's fission products, uranium, plutonium, other what's called transuranic elements, and you can store that, and it's a lot more manageable. It decays within an order of like hundreds of years, which is manageable, versus the once through cycle where that spent fuel is stored for really essentially eternity, right? It's going to be thousands of years. So the closed cycle seems like a no-brainer, but it's really expensive and complex. So U.S. policy has been to do once through. It's a lot cheaper, but it's not really sustainable. So sort of your trade-off. I'm going to let this slide's graphics do the talking mostly. You can just see pool type means that the primary system loop, or whatever it is largely in a giant pool of the coolant. And then a loop type is what we've been looking at this whole presentation, and what you've dealt with probably exclusively, unless you've done any work at the research reactors like OPAL or HIFER. Okay, this is a term you probably will only come across if you are looking into R&D things or talking to DOE people, for example. TRISO is sort of short for tristructural isotropic. So this is a coating. So it's designed to really retain fission products at very high temperatures. So if you're able to capture and protect everything associated with the dangers of nuclear inside the fuel, then you've got a very, very safe system, right? So this is sort of your first line of defense, and in some cases, maybe it could be your only line of defense. I don't think that's really practical, but some people say stuff like that. So this is made up of some materials, and it coats the fuel kernels, and you know, it's designed to expand in all directions and keep the fuel protected. This can then be basically manufactured in a couple of ways. You can put it together in little pellets and then feed that into a prismatic block geometry and have a core designed like that, kind of similar to what we've been looking at so far today with these slides. Or you can actually have that put together in a little sphere, kind of like a billiard ball sized sphere, and they call that sphere a pebble, and the core becomes what's called a pebble bed reactor core. It's kind of like a gumball machine. So this thing can be refueled online. So a machine would take one of these spent pebbles and pull it out, and then it could pop in a new fresh fuel pebble. So there actually has been a pebble bed reactor in operation. So that's not like a fantasy design. That thing has actually happened before. All right, I think this is my last or next to last slide. Again, this is a term that you might only encounter if you're dealing with R&D things, especially as it relates to advanced reactors. HALEU, they call it, high assay low enriched uranium, HALEU. This is anything that's between 5 and 20% enriched with uranium-235. Just for reference, and anybody who's you know, worked with the Navy or even ATR, Advanced Test Reactor in Idaho National Laboratory, you know, those might be enriched to like 93 to 97%. That's really high enriched uranium. But HALEU is anywhere from 5 to 20%. Right now, there really isn't a way to get your hands on it, so to speak. What you do is you've got to basically down blend the government's high enriched uranium so that you can get it down to HALEU range. A company called Centrus Energy is actually right now under a contract with DOE to be able to have this capability. So when you have this fuel, you can achieve the things that microreactors and advanced reactors want to do. You know, have a very small and efficient core design, operate for a very long time, and use the fuel better than what we do today. So if you're not able to solve this problem, to have HALEU and also have, you know, the chain available, the supply chain for this, we can't really see those reactors becoming a reality. So this is an important thing to just be aware of. Obviously, we're not fuel people, so there's not really a whole lot for us to do, but be familiar. So just keep that one in your back pocket. When somebody says HALEU, you know what they're talking about. And I believe this is my last slide. These are the two projects that we have right now that are, I'd say, the most relevant to these talking points. First one we started actually as a phase 1 in summer of 2014, and we're going to end it next August 21. So this is instrumentation and control design for small modular reactors. The project has really evolved into supporting developers like NuScale Power address issues with sensors and cables as it relates to their unique design, an integral reactor. How is that challenging existing technologies like sensors and cables? What do they need to do to accommodate that, and making sure that we have the test methods and expertise so that when they want to build one of these things, hopefully before the end of this decade, we are there to service it and support them just like we do the large-scale reactors around the country. So that's a good opportunity for us, and we've been able to partner with them on that. So if you're interested in learning more about NuScale or what we're doing, come and stop by and talk to me or talk to Edwin or anybody that's involved in that project, and they'd be happy to clue you in on it. Second one is a phase 1 that we started recently, online monitoring for microreactors. So these are the very, very small reactors that people like Department of Defense or very remote small communities want. And they don't want a lot of highly trained operators and staff on site. They want it to basically be a small self-contained power facility that gives them electricity and they don't have to worry about it, right? You know, it could do its own thing. It can operate autonomously, they say, and control itself for 10 years, and then you just shut it down and replace it with a new one. That sounds great, but that's a challenge. How are you going to operate something autonomously? It's really going to come down to sensor data, you know, and we know sensors, and we know data collection and analysis and online monitoring, determining whether or not there's a fault in the sensor, in a component, in a plant process. So that project is geared towards developing the capability to enable online monitoring for microreactors. We're hoping to work with the Oak Ridge National Laboratory. They're doing some interesting work. There are reactor developers that are engaged in other DOE-funded research projects. So there's a lot of opportunity and interest within the industry on microreactors. With the interest of the Department of Defense, people believe that these can get to reality even faster than SMRs, because when the Department of Defense wants something, they're going to put a lot of time and attention, and have actually led a couple of projects, or at least offered solicitations and awards to companies to develop a prototype in the next 3 to 5 years. So they're very serious about that, which I think is a is a very hopeful and optimistic news. So I think that's my last one. Let's make sure. Yep.